Just wait a second. Okay. So today we have Loureiro. He's currently based at the University of Edinburgh. He's a senior scientist in the Euclid collaboration and a research fellow at the University of London. And we're going to be talking about Bayesian hierarchical inference of post-sky cosmic shear data to us today. So
thanks everyone. It's great to be finally in a seminar with real people. So this is my first post happening in-person talk. So if I am stuttering or a little bit awkward, that's the reason I haven't done this in a while. So I'd like to thank Carl for really inviting me to be here today. It's a pleasure. I've been in London for 7 years and I've never actually been in here. So walk state, it's great to be here. Yeah, so I want to talk to you today about this work that we've been doing with some great people over a few years. So we have some people in Imperial, Alan and Andrew, so as Elena and Javier in Leiden, and more from UCL. It's been a collective effort to get to these results that I will show you today. I hope I managed to explain how exciting this is for the future of galaxy surveys analysis. So, is it working? Yeah, it's okay. So I'll start with this spoiler-free summary. I'll just give you a brief introduction on cosmic shear and how we traditionally do data analysis in cosmology. This is just to put a basis so we're all on the same page. Then I'll try to explain to you a brief overview of Bayesian hierarchical models and what is field-level inference, if you've never heard about this, why this is interesting, and why we think this is the next big thing to do data analysis in cosmology. Moving on, I want to present to you our Bayesian hierarchical model for data analysis on the sphere, and I will explain how hard it is to sample such high-dimensional posteriors. And finally, I'll show you an application for a stage 4 galaxy survey, more focused on cosmic shear for this case, but this is kind of a generic model that works for different stuff. I'm censoring here something that I think would be interesting to show. So it's spoiler-free summary. And then to show you what the next steps are to open for debate and anything after the talk. If you have any questions, if I'm saying something that doesn't make any sense, if I'm speaking too fast or too slow, let me know. You can interact with me. I'm here in person. All right. So our main motivation in this work is to push cosmological analysis beyond the traditional summary statistics 2-point, 3-point analysis, right? We want to move away from these old school vintage things, and we want to push towards an optimal analysis of everything our galaxy surveys from the next generation will provide us. But we want to do this while also keeping the ability to do systematic contamination checks. So not just throwing into a black box and getting whatever the machine learning algorithm told us, nothing wrong with that, but we also want to check if something went wrong along the way. Okay. All right. So let's start with this very brief overview of cosmic shear and standard analysis in cosmology, sort of in the same page. So some of you may know, cosmic shear is an analysis that allows us to understand the distortion of background galaxies through the foreground matter, baryonic and dark matter, that is between us and these galaxies in the background. So studying these micro distortions that we have in the galaxies in the background, we can probe the growth of structure parameter S8, which is sensitive to the sigma 8, which is the amplitude of matter fluctuations parameter, as well as the total matter content of the universe. We also can understand the distribution of matter along the line of sight by studying the weak gravitational lensing of galaxies in the background. This is the 2-minute introduction to cosmic shear. All right. So what is the standard vintage way that we do cosmological analysis in the big galaxy surveys? Right? You take your galaxy images and you extract some galaxy shapes. From these galaxy shapes, you use some sort of estimator to obtain a galaxy shear maps. And here, so it doesn't sound like I am being disrespectful to this way of doing cosmology, I'm using my own paper as an example. From this, if you apply an estimator, in this case a pseudo-scale estimator, extract a 2-point function, do your fit, you throw everything after you calculated variance into a likelihood analysis, and what you get in the end is the classic cosmological banana from cosmic shear, showing this degeneracy. There is a well-known degeneracy between omega matter and sigma 8. It's fun. So in case, anyone's interested in the details, there's a QR code here you can scan, and it will take you to the archived version of the paper. The same can be said and done in the CND, right? So we throw our telescope into space or in the North Pole or South Pole. We do some sort of estimation to obtain a clean map, and from this you apply your favorite 2-point or 3-point or n-point estimator. You get something, throw it into a likelihood. It's lambda CDM. Surprise! For fun. But we've been doing this for, I think, a decade or two now. It's fun, but we know that there's a plethora of information that we're not actually using. But it works, right? And so why do we want to change the players if the team is winning? I think I want to try in this next step of the talk to try to convince you that there's interesting stuff happening. So this is the vintage way, right? 2-point functions, whatever. Let's see. This is the Bayesian hierarchical way. Start with, for example, in cosmic shear with your galaxy shapes. By a hierarchical model, you get cosmological results, right? So before I get into details, I think this is a plot that motivates quite a lot this kind of approach here. So this is a work by Untitled Chapter and others, where they compare the traditional way where you get 2-point functions, CLs in this case, with what you get from this field level inference Bayesian hierarchical model called Borg. That not only you get better results with the same data, better constraints, more tighter constraints, but you also break the degeneracy of the cosmic shear. There's a classic problem in cosmic shear. So I think this is, from the cosmic shear point of view, motivation enough to do this kind of stuff. But we also want to do this having these intermediate products like the maps and the power spectrum as a byproduct, so that we can do systematic analysis to check if there's contamination in the data. All right, so quick interlude. So we can move on the crash course on directed acyclical graphs. And this is the only time I'm going to say these 3 words. I'm going to call them DAGs. Now on, they're very hard for non-English speakers. And how you can use DAGs to understand better or build your own Bayesian hierarchical model. Okay, so let's start with a very simple example. This is a classic example. We want to understand what is the probability of you waking up feeling joy, feeling happy in that moment, right? And direct acyclical graphs, so DAGs help you build these conditional and nested probabilities in Bayesian statistics that will help you understand better your Bayesian hierarchical model. So we started with our probability of feeling joy, it's probability of J, and we know that this will be conditional on our night sleep quality. So I slept on the couch, that's it. Good. And the probability of the weather. The probability of the weather itself depends on the probability of your season. So in DAGs, we call these root, these 2 quantities, N and S, that don't depend on anything, as our root nodes or our root parameters, right? And now going from the bottom up, we can build the full conditional distribution, right? Where we have, also we can have some stuff that will actually affect our the distribution that we're looking. We can have some independent variables. So we can write from this vector graph the probability of E, S, and J, which would be the probability of youth and joy given the night quality sleep and the weather, times the probability of the weather given the season, and then the priors that we have in N, the prior in S, and obviously P of E doesn't go there because it's 1.
Doesn't that reduce J?
Sorry?
Doesn't that reduce J?
It doesn't. It's just 1. It's always there. It's independent. Anyway, okay. So now that we have this crash course, I want to show this work from Leclerc and Al Heavens from last year, where they do a toy model comparing a field level inference with a 2-point function and a likelihood-based analysis, or the traditional cosmological analysis, versus the new game in town that all the cool kids are doing, which is the likelihood-free inference, which I really dislike the name. There is a likelihood somewhere. It's simulation-based, where you simulate all your effects and you do some summaries and do some sort of metrics to see if you're building well or not your full posterior. Okay, so here, if you want to give some names to these parameters, if you want to do some sort of analogy, we have some parameter beta that will affect the parameter G that affects your field F. So you can see beta as some sort of cosmological parameter like S8. Well, you have alpha to be a parameter that affects directly your field, so something like F and F. So when they compare these 3 approaches to this toy model, what you find is that the field level inference has an excellent accuracy as well as an excellent precision. It's bang on where you are. You extract way more information. You're just statistically forward modeling the fields, the statistics of the fields, and the parameters. Okay, this is a very idealized. Take this with a grain of salt. Obviously, moving on towards cosmic shear from 2015, and this is one of the papers that motivated this work from Justin Olson. This is the end goal of Bayesian hierarchical models in cosmic shear. You model everything from your PSF instrumental noise to your galaxy characteristics, all the way that you have a probabilistic distribution on your photo Z's given true photo Z's that you have here, everything about how your PSF is affecting your shears, all the way to cosmology and how your cosmology affects your fields, and you forward model everything all down to the principal level of the data. Sure, great, but this is very hard. Very, very hard. Very, very, very. So what we want to do is to focus on a subsection of these first, and to get to a point that we're convinced we can actually start applying this for the next generation of galaxy surveys. So then let me introduce you to the Almanac Bayesian hierarchical model. Almanac is not an acronym for anything, I just don't like acronyms. And so this is a Bayesian hierarchical model for data distributed on the sphere. So I'm going to focus on the Stockholm spin 2 fields, but the method works for spin 0 fields like CMB temperature or galaxy clustering. For spin 2 fields, we have CMB polarization or cosmic shear. The reason why we focus on cosmic shear first is that's more challenging. Because you take your map of the ellipticities of galaxies and you break them down into the Stokes parameters Q and U, which then translate in harmonic space into a B mode and a D mode map. Right? And the reason why this is challenging is that from the lambda CDM paradigm, we don't expect any B mode signal. And so the challenge is in having a model that works with a signal to noise that is very, 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 very low, basically 0. That's why we decided to tackle this head on first. So you don't have this problem with 0 fields. All right, so in our model, the free parameters will be every single mode of the ELMs and the BLMs. So every single harmonic, spherical harmonic from our decomposition of the map, as well as the covariance of the fields in space, which is the angular power spectrum. Okay, So turning now to the DAG for this model, which you can break down as the probability of the maps and the CLs given the data and noise into other terms that I'm going to just now show you from the ground up in the DAG, because these DAGs you should read from the bottom up. Okay. So starting with the data, we then have the likelihood of the data given the maps in harmonic space, the ALMs, and the noise, which is just a simple Gaussian. Then following, we have the probability of your ALMs given your CLs, which is an inverted Wishart distribution. And finally, a flat prior on the CLs. So far, we haven't yet pushed to the cosmology. This is already challenging enough, because what we're talking here is around 10 to the 6 to 10 to the 8 parameters. This is the MCMC 10 to the 6 to 10 to the 8 parameters already. So heading cosmology to the rest. Still gonna take a little bit more tweak.
It's only 6 more parameters, sure. What's 6 out of 10 to the 8?
The problem is the Boltzmann solver dominates that, and that is wrong. So that's something, and also because we're using Hamiltonian and CARLO, we need the derivatives. So taking that cue to get to the point there. Okay, so how do you sample high-dimensional space? And this is the Hamiltonian and CARLO. Never heard of Hamiltonian and CARLO. The idea is that you now transform your MCMC into a dynamical problem. We have now a particle that is in n-dimensional space, n dimensions being all your free parameters. And you get your particle over there, you use your negative log posterior as your potential parameter, and you dynamically evolve the Hamilton's equations. You check if you lost energy or not. If you did, you might throw away the point. If you didn't, you keep the point, flick around randomly, see where your particle ends, and you repeat the process. Because this is such a high-dimensional space, Hamiltonian is extremely efficient for this kind of problem, because it evolves the system dynamically every time you reset your momentum, which is just basically a random flick in a different direction. Okay, so if you're wondering, this is what I showed you this before in a different form. This is what our potential looks like. It's a bit of a mess, but we have a little bit of a problem. Is the angular power spectrum, or the autocorrelations of the angular power spectrum, they need to be positive. What you get when you look at this example with a very low signal to noise in the ALM and CL parameter, like just marginalizing everything, just looking at one of those, you see we have this flame-shaped posterior, which is very hard to sample. And also doesn't solve the problem that the CLs cannot be negative for the autopower spectrum. You always expect to have positive correlations for those. So one naive solution is to take the log of the CLs, then you're not going to have any negative values in your parameter space. However, you turn your problem from a flame posterior that is hard to sample into this evil stingray posterior, which is really hard to sample. As you have a lower and lower signal to noise for B modes, for example, you get into this funnel regime here, which makes your sampler very inefficient. It's very hard to get there. But luckily, similar problems have similar solutions. And this problem is known in the probabilistic programming community as the Niels funnel. And something that happens inherently when you're trying to grow a certain quantity and also the covariance matrix of the quantity. So in our case, it's the maps and the covariance matrix of the maps, which are the CLs of the angular power spectrum. So we found our analogous solution to this problem based on the new funnel problem, which is taking what we named the pseudo log of the CHOLESKY decomposition of the covariance. Because the problem has a solution which is taking the CHOLESKY decomposition, but we had an extra problem, which was that CLs positive. Then we do these change of variables here, where we take the CHOLESKY decomposition in the diagram, we take the log, or otherwise just take the regular values, and we rescale our maps by the square root of the covariance matrix. and then you have to recalculate all the potentials, all the Jacobians, all the first and second derivatives of that. But this makes a hell of a difference. So here I'm showing you the histogram of the posterior and the log posterior tracer. If you look at the naive coordinate system, it's really bad. It takes a lot of time, runs, change. It's really bad chain. When you do the Cholesky transformation, you get to something that is way more reasonable. We can also look at something that is called Bayesian fractional BC information. That is a way of telling you how well your Hamiltonian Monte Carlo is exploring the phase space or your whole posterior space. What you expect here is that both these diagrams should be very similar, or the BFMI to be close to 1. So look at the naive parameterization. This is horrible. Don't ever want to publish this. But the new parameterization, it's actually solves a little bit of the problem that we're having with exploring our posterior distribution.
Sorry, what's E and delta E?
So this is the energy and the difference in the energy that you have in your, because you're evolving Hamilton's equations, you have a potential energy and a kinetic energy. So the energy is just the sum of the potential. Delta E is the difference between steps.
I see.
Yeah, so it's basically that solved one problem, which was that we were not efficiently sampling such high-dimensional space. The other problem we had was because it's such a high-dimensional space, we had very long correlation lengths in our MCMC. So in an MCMC, all the close-by steps are correlated because all depend on each other, but we expect that this correlation over time loses the memory. So it's very important to have very low correlation lengths in an MCMC. The problem is very high-dimensional, so it's very hard to tackle this down. And it also takes a lot of time to run it. So we developed these Hamiltonian Monte Carlo tuning. Just for start with a burn-in using the square root, the inverse square root of your Hessian, your posterior, which is calculated analytically as the step size proxy. So this tells you a lot about curvature that you have in your potential. And because in this problem, the posterior is unimodal in every single dimension that we have, it's okay. So we start with that, we do the burn-in, we find the region of interest where most of our samples will be taken from. And we start a tuning phase. We're still using the Hessian, we run the sampler for much longer. So we have some sort of idea of the actual curvature of the posterior close to the peak. We then take the standard deviation of the samples, we reset everything again. And if you've ever done Hamiltonian Monte Carlo, you know that there's a lot of free parameters. So tuning all these free parameters by hand is a lot of wasted time. So we've developed these leapfrog tuning that will rescale again all the step sizes in a solved for factor, such that we can reach this target acceptance ratio. For example, like 85%. So you can do to set your target acceptance ratio, you don't have any more free parameters. So there are things like the step size of the leapfrog, or how many leapfrog steps do you take. All these is fixed by these tuning phase. So then finally, throw everything away again. We reset your sampler and we take the samples. And this has been crucial to take down the correlation length that we were finding for this problem. So here is exactly the same simulation, exactly the same random seed. The only thing that changes here is doing a tuning or not doing the tuning. And we managed to tackle down, this is a very low dimensional case. Right. And in this case, we managed to tackle down like almost by a factor of like 4. So the length of the correlation. This means that now, instead of having to run this for 30 years, for Euclid, you can do like 5 or something. And you know, yeah, it scales in a weird way. But it was fundamental for us to make this problem feasible. So how feasible is it? So I want to show you now the results from a 4.21 million parameter MCMC. So this is for a Euclid-like survey with two tomographic cosmic shear bins. We have E1, E2 for the first bin, E1, E2 for the second bin. So these are the components of the lattices of the galaxies. We're probing a multiple range from 4 to 1024. Still not ideal for the next generation of surveys, but much better than we could do before we figured out that those things about the coordinate system and about the tuning. So from these 4.21 million parameters, 10,000 of them are the angular power spectrum. So yeah, we're doing everything on the mask side. These are just showing the power spectrum of the mask, the input signal to the simulation, the realization of the simulation, and the noise levels for the input modes. So if you look at the B modes, the input B modes are much lower, right, than the noise that we're going to get on the survey. This is what the data looks like. So where you don't see any data is because we have a mask. So this is the first component of this shear elasticity. There's noise there. It's a mess. Can't do much with this. But then we run Almanac, and this is showing you the marginalized angular power spectrum. Good contrast, but if you can show you. So the input to the simulation is the red dashed line. You can see there. It's my mouse. Yes. Okay. So the input to the simulation is the red dashed line. The blue dark thing is the standard approach people take, like the pseudoscale estimator, just measuring the data. It's noisy. There's mask effects. And what we cover, which is terrible to see over there, is this shaded region that shows you the 68 and 95% confidence intervals. There's a little blue line with a white outline here, which is the mode of the distribution, and every single step. So every single step L, you marginalize over everything. You take the 68, 95 and the mode, and we can recover the anchor prospect from those maps without the mask effects, without any. And also recover the B modes, which are a great proxy for systematic elimination. So even though the signal is basically 0, we can set an upper bound to this quantities. Another thing we can check, obviously, is any parity violating modes. So in cosmic shear and most of the physics, you don't expect any crosses between A and B. If you do see anything there, the systematics lurking into your data. So we can see this. And not only that, right, but we also have the posterior distribution for all of these things. So it's not just a point estimate. This is just for visualization, but all of this is 4.21 million space. Another big problem in not only CMP, but also not only CMP polarization, but also in cosmic shear is the ED. So when you mask part of your sky, some of the modes that you're observing will be ambiguous, such that a low B mode can be translated into a high E mode, or vice versa. And this is very problematic for cosmological analysis, because you can bias your cosmology quite badly from this. The good thing is with Almanac, because we have all the distribution over all these parameters, we can check this leakage by fixing the multiple and checking the pairs of E and D. And so we produce these kind of avocado plots that are good news for Euclid. It doesn't look like our mask geometry in the last data, the final data release will introduce any leakage. But basically, if you had any leakage, you would see a banana instead of an avocado. And then what you can do is marginalize over that, throw it away, doesn't matter, do cosmology with the rest. We know this information now, we can use this. And then the cool things that we get, because we're probing like your parameters also the clean shear in the pixel in the sky, the denoise shear. So here you're showing the fiducial simulation. So that same simulation I showed you before, turning off the mask, turning off the noise, what we get. And when you recover an almanac are samples from these, from the denoised map. If you look at the mask, you can see that where we have data, the sampler can actually, the code can actually probe very well, can constrain very well to denoise shear maps. I'm just sharing the second in. Where we don't have data, Almanac can try to reconstruct the underlying structure. Obviously, the small scale structure is not going to be able to recover because we don't have information on that. But one of the advantages of doing things in harmonic space, which is usually a disadvantage, is that by including a mask, you will correlate a few of the modes, the adjacent modes, because of the mixing of these modes. Because these modes are now correlated, where we do have information, this correlation helps us constrain what is under the mask. So again, bonus, you can get mass maps and convergence maps from this as well. We are saying basically the same ALMs, it's just a linear transformation. And you also have errors from the mass maps, which is fun. And this is a cool sample check where you get the best fit map you have from your samples. You just take the simplest pseudo CL estimate from it, which is now full sky and denoised, and you compare with the realization of your input simulation with no noise, no mask, no anything, and they match really well. There is a lot of noise, obviously, in the high Ls, because there's a lot of noise in the data, but still the match is really good. And I'm still investigating how good it is that we are able to recover the large scales very well. This is some boring convergence statistics, just showing that the chains are converged, everything's working well. We have an average correlation length of 100 for total sample size of 336,000 samples. Our boring convergence diagnostics. This is the Hansen statistics, checks how your gradient is around your posterior. And yeah, this is it for now. Summary, field-level inference is really cool, extremely powerful. It is one of the optimal ways of extracting information for our cosmological experiments, although it's extremely challenging to get it to work on real data. But Almanac can recover the full sky posterior high resolution maps and the angular power spectrum of them. There were several tricks that we had to learn along the way to be able to get here. But we got here and we can still do systematic contamination with Almanac in this very powerful way. What's coming next is that we're pushing the limits even higher. So we're now doubling the number of multiples we can get, which results in 16 billion parameter space. These chains are very close to converge. I wish they converged faster so I could show you them, but stay tuned, like papers are coming. There's more studies that we're doing about the HMC tuning. I think we can get it even better. And there's Elena's student Javier is working on comparing the cosmology you get from just using Almanac as a CL estimator with the traditional CL estimators. As I said, we're pushing the hierarchy towards adding a multi-solver. It's happening very soon. And testing with galaxy clustering and cross-correlating galaxy clustering with landing is happening, as well as application related. That was it.